Hello. So this is AMET 104 lecture recording week 2.3. So last class we talked about the exponential growth model and the geometric series. So let's recap a little bit. Exponential growth model. And we also learned about the geometric series. So what is the exponential growth model? So exponential growth model is the growth model that grows by a constant factor. So for each generation, you're multiplying the constant value on there to find the next term in the sequence. So here, the explicit formula for this was given as p sub n equals to r to the power of n multiplied by the initial population. And here, r was called the common ratio. And the recursive formula is given as p sub n equals to r simply multiplied by the p sub n minus 1. So the common ratio here is determined by r equals 1 plus r. Here, the smaller r is simply y minus x divided by x, where the x is the baseline, and the y denotes the end value. So simply, if you are given any scenario that grows exponentially, you can model using this explicit formula, recursive formula, and you can actually predict the future using this model. And last time we also talked very briefly about geometric sum formula. So we didn't really go too deeply into the geometric sum formula, but here is the sum formula itself. So the sum is basically adding the initial population all the way up to some nth population, and that is simply found by r to the power of n minus 1, so that's nth population, minus 1, and you multiply by p to the power of 0 over r minus 1. So let me quickly tighten it up. So now, knowing this, we can simply go back to the initial example that we started off yesterday. So the this option 2, where we had you receive 1 penny on the first day, on day 1, and you receive 2 pennies on day 2, and you go all the way up to the 31st day. So here we can see, we found that on the 31st day, so on day 31, we actually have found that you receive the R to the power of 30 multiplied by the initial population. In this case is 1. So let me just write that. And this here is initial population. And this is simply 2 to the power of 30. And the number was 10,737,418 and 24 cents just on that day. So if you actually add up every single pennies that you receive on each day, you will actually end up with, you can simply now find that using the geometric sum. So the sum here would be, we know that the growth rate is 2 and to the power of 30 because it's 31 days, minus 1 multiplied by 1 penny divided by 2 minus 1. So here 2 is the growth, common ratio. So if you put this into calculator, you will actually receive 483,647 cents. And that is actually the same as saying 21,474,836 and 47 cents. And that is a significant amount of money compared to the option 1, where it only gave you the $100,000. So today I am planning on going over a few different examples that you might encounter solving homework assignments and quizzes and even exams on this chapter. So let's start with something that's simple. Example. So let's say the population grows according to an exponential growth. Model, where the initial population is given as 11 and the common ratio is given as 1.25. So when the common ratio R is equal to 1.25, this actually implies that the 25% growth for each generation. So let me write the growth in each generation. So we can, so let's first find the population after one generation. We know that after one generation, we will actually have 13.75. And you can simply multiply 1.25 for each generation to find the next generation. Then how do you find the explicit formula? What's the explicit formula? So explicit formula, as we have discussed above, is actually given as P sub n equals to common ratio to the power of n multiplied by the initial population. We already know all the pieces, so we can simply substitute 1.25, make sure you put the parentheses, and to the power of n, and you're multiplying it by 11. Then now, if you want to find, let's say, the 7th generation, so the population after 7th generation, you'll be able to find that 1.25 to the power of 7 multiplied by 11. And then in this case, it's 52,452. So that was quite simple. Let's do one more thing that's very similar to this. Another example. So instead of being given these values, how about the exponential growth model has a recursive formula? So let's say you're given the recursive formula as P sub n equals to 9 multiplied by P sub n minus 1. And you're also given that the initial population is actually 8. Then how do you find, so given these two pieces, so you do not know the explicit formula, you're just given the recursive formula and you're given the initial population. How do you find the second generation, the generation after, the population after one generation? So if you want to find a P sub 1, we know that you simply have to multiply 9 to the initial population, which in this case, it is 9 multiplied by 8, and that's 72. And P sub 2 is simply 9 multiplied by P sub 1, so that's 9 multiplied 72, and you'll receive 648. Let's do one more. So P sub 3 is actually 9 multiplied by P sub 2, and we have here found that the P sub 2 is 9 multiplied by 648, and you should end up with 58,032. So from this, you're given the, knowing the recursive formula and the initial population, you could also find the explicit formula. So it's P sub n equals, we know that the common ratio here is 9, even though this is not given in the problem. And you will get 9 to the power of n multiplied by 8. So now let's look at an example where the common ratio is not necessarily increasing. So far, when we looked at these two examples, we only looked at the growth. So the first example, we had 25% growth. Second example, it actually had 800% growth. This is because R is actually 1 plus R. This is the growth rate. And if this is 9, the growth rate is actually 8. So this is 800% growth. So let's look at an example where it's not actually growing, it's actually decreasing. So example. So a population and I'm going to use the word decays. According to an exponential model where the initial population is given as 3,063 and the common ratio is given as 0.84. So here we should understand that since the common ratio is defined as 1 plus the growth rate, when this all thing equals to 0.84, this actually implies the growth rate is negative, not the negative, yes it is, sorry, negative 0.16. So this actually is the same thing as saying 16% decrease. So you're seeing 16% of the decrease of the population for each generation, or you can also say it's a negative growth. So as we have mentioned before in the previous lecture, if the common ratio is in between 0 and 1, so if it's given as some decimal or fraction that's less than 1, it is safe to assume that this is a decreasing model or decay model. So now we already know the initial population and the common ratio. We know that the explicit formula can be found as P sub n equals to 0.84 to the power of n, and you're multiplying by 3,063. So that is the explicit formula we can establish just using whatever you're given in the problem. So simply by using this, we can actually find P sub 7, and you're simply substituting 7 for wherever you see n. And this should equal to 904. So what if the question asks you, how many generations will it take for the population to fall below 200? So to find this, you're simply going to use this formula. And let's say for some n, you're going to end up with, let's say just 200. So, because all we have to find is the point where it reaches 200. And simply here, we can calculate for n. So to find n, you have to divide each side by 3063. So you will have 0.84 to the power of n is 200 over 3063. And that implies 0.84 to the power of n is actually, so this is approximately 0.6529. And this is simply found by putting this into calculator, putting the right hand side to the calculator. So here, you can approach this problem in several different ways. So as you can see, because we now have the variable, the one that we need to find in exponents, we cannot simply add or multiply or subtract to actually find what it is. So there are a few different routes to take. You can either formally you can use a logarithm, but in this case, in this class, I'm not going to go over the logarithm. That's for a little more involved classes like calculus, pre-calculus. So in this case, instead of using the logarithm, we're going to simply use 0.84 and try different powers. So we're going to first try the second power, third power, fourth power, and see when it actually becomes less than this value. So if you're simply repeatedly multiplying this 0.84 to itself, you will actually find that when n is 16, we will have 0.84 to the power of 16 is actually equal to, it's approximately 0.06144. And that is actually the point where it is less than this right-hand side. So I know this is not a very logical way of going about this, but when you receive problems like this, you will not receive an n that's so big that it's going to take you forever. So you can simply put it in your calculator and repeatedly press the answer button to actually get to this number. So this implies after 16 generations, the population will actually fall below 200. And that's actually the end of this problem. So let us now look at a few examples that are more applicable to real world. I mean, we have been using all the tools that's actually really useful in real life, but let's put it into context. So, example, let's say a crime in a city is on a rise. And each year, the number of crimes committed increased by, let's say 50%. I know it's a huge increase, but just so we can see the actual increase in the difference between each generations. So now let's assume that there were, so let's say there are, let's say there were 204 crimes in 2019. And let's denote P sub n be the number of crimes committed in 2019 plus n. So this actually may look a little confusing. So what this means is, this simply means that when n equals 0, you plug 0 here. So what will happen is P sub 0 is the crimes committed in 2019, because if you plug in 0 here, it's going to be 29. So when n equals to 1, this implies this is a piece of 1 now. And this is the same thing in 2020, because you're simply plugging in 1, and equals 2. It's going to be P sub 2, and that's going to denote the 2021 crime, and so on and so forth. Does that make sense? So we already have the 50%. Oops. We already have the 50%. And that's the growth rate. So knowing that the growth rate in this case is 50%, and knowing that this is growing exponentially, we can find the recursive formula. Let's say in this case, for this model, as well as the explicit formula. For this model. So how would you do that? So in order to find the recursive formula or explicit formula, you actually need to know first the initial population. But in this case, we know that in 2019, there were 204 crimes. So we know that the P sub 0, the initial population in this case, is 204. And the second piece that we need to know to find this formula is actually the common ratio. So how do you find the common ratio? So before, we have defined the common ratio is simply 1 plus the growth rate. And we know that the growth rate here is 50%. And we know also that the 50% in decimal is, let me put this way, decimal is 0.5. So knowing that now the growth rate is 0.5, you can simply plug it in there to actually find the common ratio is 1.5. So let's find the recursive formula first. So recursive formula we know is simply multiplying the common ratio multiplied by the previous term in the sequence. And what about the explicit formula? So explicit formula is the common ratio, and you're exponentiating by n, and you're multiplying the initial population. So in this case, it's going to be 204. So that was quite simple, right? So we found the recursive formula and the explicit formula simply from this example. So in this example, we weren't given the common ratio, but we were given growth rate. And using the growth rate, we were able to find the common ratio. And since we were already given the initial population, it was pretty intuitive to do so. So let's say, knowing all these facts, using this model, how many crimes will there be in, let's say, 2029? So in 10 years from here. So in 2029, how many crimes will there be? Obviously, we haven't been to 2029 yet, but using this model, we can actually predict the future, and it may not actually be exactly, it may not be precisely on point, but being able to predict the future using the mathematical model is very, very useful in real life, and it's used all the time. So in 2029, what is the end? What's the generation in 2029? So knowing that we have defined 20 as a piece of n to be 2019 plus n, this is simply saying that n is 10. In other words, this is 10 generations after the initial population. So after 10 generations, simply this is saying the p sub 10. And if you plug this into the explicit formula, sure, you can find it using the recursive formula, but that's going to take longer time. You can simply plug in 10 multiplied by 204, and obviously we will need the calculator to find this, and I think it's going to be 11,764. So from what's important here is that even though we can find both recursive and explicit formula for this specific example, knowing which one to use to save you some time, even though you can actually find this value exactly the same value using the recursive formula, knowing what's more efficient is a key thing here. So problems like this, so modeling in real life, something that's growing exponentially or decaying exponentially, is a very useful factor. And I know I've used the some random example that's not really likely. However, in modern days, it's actually quite widely used in the spread of the virus or eradication of the virus, or like a COVID-19, even though I'm not going to use an example of COVID-19 because it's a very sensitive topic, but or spread of the bacteria, or anything like that, anything that grows exponentially like that. You can actually use this modeling to predict the future, and so you can actually be better prepared for the future. Let's now try to find some other example that will be a little bit more different. So let's do one more example like this before we do a few more examples about like on the geometric sum formula. So let's say in (2019), the number of math majors, so let's say number of math major students, let's say at, let's say UAlbany, was 426 students. And in 2020, the number of math major at UAlbany is now 465. And you're asked to find the growth rate. So do we all remember how to find the growth rate? So growth rate, the small r, is simply y minus x over x, where y is the end value and the x is the baseline. So here we are trying to find the growth rate from 2019 to 2020. So in this case, the baseline x is actually 426, and the end value will be 465. Then you can simply plug it in to this formula to find that the end value 465 minus the baseline, which is 426, and you're dividing everything by 426. When you're plugging this into calculator, make sure you do the numerator first, because there's a negative in there and you do not want to confuse the system. And if you plug this into a calculator, you would receive something very similar to this implies the approximately 0.0915. And that is actually the same as saying it's 9.15% growth. And this notation I've already used a few times is the approximately. Okay, so now we've covered a few different examples, growing models, decay models, and we've also solved the word problem, and now we have found the growth rate. Let us now do an example involving the geometric sum formula. So let's consider the sequence that goes like this: 7, and the first generation is 42. Third generation is 252, and so on and so forth. So knowing that this is the geometric sequence or the exponential growth model, how do you find the common ratio? So how do you knowing the generations, how do you find the common ratio? So we can actually find that if these were exponential growth model, we know that recursive formula would go like, oops, the recursive formula would go something like this. So this means if this is 1, sorry, if this is 0, sorry, if this is 1, this will be 0. And we can simply divide the piece of 0 on each side to find that the common ratio is actually piece of 1 over piece of 0. And we already know the piece of 1 is 42 and piece of 0 is 7. So we can simply plug in the 42 and 7 there to actually find the common ratio, which in this case is simply 6. Then how do you find, so now you know the common ratio is 6. How do you find the piece of 0, piece of 1, plus all the way up to, let's say, piece of 12? How do you find this? So this is where the geometric sum formula comes very useful. So let's recap that. So geometric sum is a sum where you start from 0, P1, and all the way up to piece of n minus 1. And that's simply going to be the common ratio to the power of n minus 1, and you multiply by the initial population and divide by the r minus 1. So here, since we have 0 to 12, we know that this sum is going to be r to the 13. This is 13 because this is 12 and there are 13 terms. Minus 1 multiplied by P0 and r minus 1. And we actually know every single variables here, and that is 6 to the power of 13 minus 1 multiplied by 7, which is the initial population, and you're taking 6 minus 1. And if you plug this into calculator correctly, you will end up with, I think, 18 billion and 284,971,621. So in most cases, if this was an in-class lecture, if this was a face-to-face lecture, I would have accepted answers like this. I know this is a very big number, and oftentimes going from here to here, by simple error in input and calculator, you may end up with a wrong answer, and I think that's very unfair for you. So in normal circumstances, I would have accepted answers like this, but because now you can actually check your answer several times, and also the Pearson system will also tell you if you're correct or not. So you would actually need to practice using the calculator correctly and actually get the answer in precise manner. So let's actually do one last example before I call it a day. So let's do the same type of example, but now with a different numbers. example. So consider the geometric sequence where now it starts from P0 with 64 and P sub 1 is 16 and P sub 2 is 4 and so on and so forth. So do you notice that it is now a decreasing sequence? Instead of increasing like previous example, it is actually decreasing for each generation. So how do you find R? So previously we have found for some R, whatever this is, we know that P sub 1 is defined as R multiplied by P sub 0 because this is the geometric sequence. So using this, we previously have deduced that we can simply find the common ratio as P sub 1 over P sub 0. And in this case, we have P sub 1 as 16 and P sub 0 as 64. So that is what? That is actually a quarter. And you can also express that into decimal form like this. And knowing this, we could also find that this is actually 75% decrease for each generation. So now we can actually take these two pieces and just conclude that the common ratio is actually 0.25 or a quarter, whichever you prefer. So now let's find the sums. Let's say up to 7. So you're going from 0, 1, 2, 3, 4, 5, 6, 7. So knowing that knowing that the common ratio is 0.25 and that the initial population is 64, and also knowing that there are 8 terms, we can actually use the geometric sum formula as such. So let's actually rewrite the geometric sum formula so you can get used to all these numbers. So over R minus 1 is the geometric sum. And now what I'm going to do is simply plug in everything I know. So R is 0.25 to the power of n. So n here is the number of terms. So there are 8 terms. Minus 1. And you're multiplying it by the initial population, which in this case is 64, and divided by R minus 1. So 0.25 minus 1. I know this may look complicated, but it really isn't. Just because there's a decimal doesn't make it more complicated. But if you plug this into a calculator, you should actually end up with 85,332. And that is the answer. So today, I'm actually going to call it a day and the class here. Next class, we're going to go into a new big chapter. It's going to be chapter 10. And chapter 9 was very closely related, especially the geometric sequence, the one we just did, because we're going to do some financial mathematics and learn how the money works in the system. Okay, well, thank you for listening. Have a great rest of the day.